Buongiorno a tutti. Allora, innanzitutto ci tengo a ringraziarvi a nome ovviamente della sezione di Catania, dei laboratori del Sud e del DFA. Siamo tutti e tre organizzatori di questo seminario sulla meccanica quantistica. Quest'anno, come sapete, è il centenario della meccanica quantistica e noi lo onoriamo con un seminario del nostro Marcello. Marcello, non hai bisogno di presentazioni, però ci sono in sala anche alcuni più giovani. Marcello è uno dei pilastri della nostra comunità, in particolare della sezione di Catania. No, perché è la verità, continua ad essere uno dei pilastri della nostra comunità, della sezione di Catania in particolare. Se non ricordo male, sei stato uno dei primi degli assunti della sezione, il primo. Per me è un onore perché io sono l'ultima in realtà. Quindi ci tengo sono particolarmente emozionata, devo essere sincera. Quindi lui è uno dei nostri pilastri, dei pilastri diciamo, del gruppo teorico. Ha un curriculum straordinario con innumerevoli pubblicazioni, innumerevoli studi sulla fisica legata alle stelle di neutroni, delle equazioni di stato, ma oggi in particolar modo ci parlerà della meccanica quantistica, in particolare di un argomento, cioè adesso ve lo spiegherà meglio Marcello, che è stato oggetto di una delle sue ultime pubblicazioni che è stata pubblicata in un'importantissima rivista. Per cui Marcello, grazie mille di essere qua. Alla domanda quanto ne sai, io onestamente allo stato attuale posso dire non abbastanza e sono sicura che alla fine di questo seminario posso dire ne so un po' di più. Quindi grazie mille e vai.
Ok. Thank you for the nice presentation. Thank you at the organizer for giving me the opportunity to speak about some publication I did. It's about a realistic model for completing quantum mechanics. What means completing, I will explain. But I want to stress strongly that I'm not questioning quantum mechanics. No. Okay, nobody can do that. I would be completely crazy. I'm a bit crazy, but not so much. Okay. So let me outlook of the seminar. I will give first an elementary introduction, not to something usually called paradox. I will call critical points of quantum mechanics. I will be here elementary. So I apologize for experts if I repeat well-known things. But I did decide to do that because I want to put in a clear way the framework of what I'm going to say, to avoid misunderstanding. I will give just a few words about Copenhagen interpretation of quantum mechanics and the need to extend quantum mechanics that are not exactly in this order, they are mixed. And then so the first part will be 1, 3. Then the second part I will present the model, how they solve these critical points, and somebody else. What are exactly the critical points I'm going to speak about? First I have to stress that the first part I will speak about the usual quantum mechanics, how it is taught and how it is presented in a textbook. So the basic concepts are quantum state and the wave function. They are bound together. The wave function represents the quantum state. The quantum state is represented by the wave function. So I will speak about wave function. And I will consider as the dynamical evolution of the system, of any system, the Schrödinger equation and the corresponding formula. So I will what is called a speakable quantity. In this framework, some critical points arise. If you put the presentation in this framework, which is the framework everybody, I think, learn quantum mechanics. Not a question. Okay, the critical points are essentially 4 plus entanglement. So first, the measurement problem. I will speak why it is a critical point. It's not a paradox. There is not a paradox. Then I will speak a situation where you can have reductions, some sort of measurement without interaction. It's a little bit paradoxical, but it's a experimental fact. Then I speak a spontaneous decay. That is a little bit surprising that I consider as a critical point, but I will explain. The classical limit poses some problem, as I will show. Diagram I'll say a few words only, because once you solve this problem, the diagram is automatically introduced. So, first critical point, just a measurement. It's called, everybody in the literature is called measurement problem. Why is a problem? So let us consider a detector, this one, the detailed description of the detector. Okay, a detector, what must be at least do? If you have a set of function corresponding to the detector, of course, to which one there is a single response, and a given response coming only from this state. This defines somehow what the minimal requirement that an object can be considered a detector. Then let us consider a superposition of this state and apply Schrödinger equation. Schrödinger equation is a linear unitary equation, evolution. So the final result will be a superposition of the result for each one. The same coefficient here and here. The superposition is concerned. What we observe is not that, at least if you consider a real detector. What detector will be a detector, what I have to do is to select one of the response here, and only one. And this is reduction called reduction, because the wave function is reduced to one component only. Then one introduces probability, which is already strange, but anyhow, probability. So the modulus square of each component gives the probability to get the result, each result. Rk with the probability 6k squared. These are observations, it's not a question to make theory. So in this case, it's clear that the Schrödinger equation is violated. So it's not valid anymore. Why? What is the specificity of the measurement? First of all, is unicity of result, reduction. You get only one result. And this is the main point. Then the result obtained stochastically. So we cannot predict which result will be of the measurement only at a statistical level. So the measurement is characterized by indeterminacy, because the same initial condition you get different result. So by definition, this is indeterminacy. Irreversibility, because vice versa, the same result, let us say Rk, can be obtained by a different combination, so a different initial state. So you cannot reconstruct back by time reversal from the result, the initial state. It's impossible by logic. And then there is some probabilistic, probability must be introduced necessary. Okay. And this is in sharp contrast with the Schrödinger equation, which is, as I already said, linear, reversible, finite reversible, deterministic, because to each initial condition there is a final state, and there is no stochastic evolution. Of course, in Schrödinger equation there is no stochasticity. And of course, then this means that Schrödinger equation is unable to describe the evolution, what happened during a measurement. The measurement it cannot be described. There is a critical point, of course. Of course, we can always solve the problem, as we all do every day, postulate all. So we consider that we don't know what happened during the measurement, but we know what can be predicted. Can be predicted only stochastically, so in probability, and unicity. That's a matter considered as a given by nature. Okay, and will give us this behavior which is intrinsic in nature. But the process of measurement is unknown. You cannot know. Let us illustrate this point because it's not fantasy. I will explain, I will illustrate that with a simple experiment, a real experiment. The schema is just the usual two-hole screen where, in this case, I will show for electrons. So electrons are impinging in this two-hole, and then the two-hole behave like a source of wave function, spread wave function because of diffraction and interference, and the output of the source is a source of a spread wave function, which can be decomposed in a different component corresponding to different location or different piece of the wave function. So this superposition corresponds to this, okay? Then we should get only one, and what actually happened. So we send electron one by one. For each one, you get a spot here. So the electron has arrived here. The wave function was spread to all space, but as we detect in a single place. This is the wave packet where we expanded the wave function. This is not a screen itself, but a monitor, which is recording each event. So in a given event, I get only one. Then I got this, or this. There it is spread all over the screen. This is reduction, right? To spread the wave function, I get only a localized one. So one component only. This spot can be considered a localized wave packet if you want. Then I continue to send electrons one by one. And then finally, when the number of electrons is large enough, I got a pattern, is a interference pattern, the stripe of the interference. So the event concentrates in some region where the wave function is large. And this is Born law. That this one is proportional to psi modulus square. So this is reduction, and this is Born law. That's a very nice illustration. And it's a real experiment. Now I'll go to the second critical point that I have to spend some time. Also, in this case, everybody knows probably, but I'm sorry to repeat. So suppose there is a splitter here, a photon is coming, the splitter split the wave packet of the photon into two components, one following the red path, the other following the blue path. They are recombined here with another splitter. So at each exit port there will be a superposition of the two. This contain both blue and red component, and so this one. So they superimpose here and here, so I can somehow regulate the distance such a way that here they interfere destructively, so there is destructive interference. So I don't get any photon here. The photon will come 100% or 2. This is Mach-Zehnder interferometer, schematic. Now, the problem comes, okay? Critical point comes if I put a perfect absorber here. So the red path is interrupted. What is observed, okay, what can happen? So the only path which arrives here is the blue one. The one is interrupted. So here we get only one photon, one component, sorry. So there cannot be any interference. But the red path is not present. So I can get photon both in 1 and 2 with 50% probability on 4th act. Okay, this means that a photon, suppose now consider one event where the photon arrived here in the port which was dark. Now it's not anymore dark because there is no interference. So there is only one component. Here at the beginning there was two components. But if the photon has followed this path, has not done any interaction with the obstruction. But here is far away, there's no interaction. So you get reduction because we pass from initial two-body component to only one component. That is, by definition, reduction. But there was no interaction. So you can have reduction without apparent interaction. If we think that the wave function cannot be modified without interaction, we must hypothesize, assume there must be some hidden interaction. And this is, of course, this is a little bit paradoxical, I would say. And this observed is not making fantasy. And as I go to the third critical point, it is the spontaneous emission. When you excite an atom, everybody knows that after a while, decay and emit a photon. This was at the beginning, considered the beginning of quantum mechanics. It was considered by Niels Bohr in his paper, original paper. Why it is a problem? Critical point. Because if I consider, again, switch off the, consider only Schrödinger equation. Okay, if the initial state of the atom is in the excited state, then how with the Schrödinger equation, how it evolves? It mixes the excited and the ground state, and evolving time. So there is one component here, one component between which can include the ground state and the photon. And the strength of this two component change in time, this decrease, this increase, this Schrödinger equation, there is nothing else. Finally, the photon arrives here and is detected. When it is detected, the atom will be the ground state. If you do this picture, so only Schrödinger equation, after the excitation, how long will it take to go be detected in here? Here is the distance from the atom and the detector divided by velocity of light. So every time I excite, the atom will evolve. I get the photon here after a time. It is L divided by C. L is the distance. Every time I excite, if I use this picture, I always get the same time of detection. This is contrary to experience, because there is, before the photon can get here and produce, let's say, reduction, is a reduction, the atom decays spontaneously, this spontaneous emission. And I need that because otherwise I don't get the well-known exponential law. We know that we have a set of atoms, we excite all, the number of atoms that are still excited after a time t go down exponentially. In this case, if I use only Schrödinger equation, I will never get it. So I need spontaneous emission, what is called quantum jump. And we have one must assume, postulate, that this occurs randomly with a constant of probability per unit time. If you assume that, you get exponential law. Probability to get to be the atom. So in the real picture, the atom will be there for a while, then they excite, emit a photon, after a while it will take here. So the probability go down, change, the time of detection change for each different decade. Okay. So one has to make additional assumptions. Postulate it. Quantum jumps exist and they follow his properties. I'm sorry to be so elementary, but it's the best thing to do, in my opinion. So these are not fantasy, of course. Quantum jump can be observed in fluorescence experiment. I don't go to details, but anyhow, it's a 3 levels or 4 levels, no, 3 levels arrangement. So there is a laser. In this particular experiment, there is a flash lamp, but it looks like a laser. So which the 2 frequencies and the system go back and forth. So there are strong transition at 2 different frequency and then wavelength, and then go back and forth. I have one observed the emission of this one and this. But if there is a weak transition to another state, from time to time, randomly, the atom will decay here, emit another photon, the different frequency, and if this is a metastable state, will stay there for a while. So these are the back and forth triangle. Emission, then suddenly, when there is this transition, is interrupted because the system is here. So it cannot go back. But this back and forth is interrupted. After a while, a long time, this will decay here and then, of course, start again to recycle. So the jump down is due to this transition, then up this transition, and you can see, well, a limited time, but anyhow, you can see that it's random. The occurrence of the transition here is random. And both random, the momentum, the time where this transition occurs, and random, the time where this transition occurs. And this figure is trivial, but looks like instantaneous. Okay. This is the time here is enormous scale, so that it doesn't say anything about the time elapsed for the transition. But all experiments are compatible with the instantaneous decay. Quantum jump looks instantaneous. So it's legitimate, I think, ask what triggered the decay, which is not in the Schrödinger equation again. Where random is coming from? It's not in the Schrödinger equation random. So what is random coming from? This is the third, so this is the third point. The last critical point is the classical limit. Why? I will show you why. Is rather than a principle, it's called a correspondence principle, but it's not a principle, it's a requirement, because our world is classical. So we cannot say. So that at a certain moment, we must have transition from quantum mechanics to classical mechanics. Usually one uses the short wavelength limit, where the wave packet can be made. If the wavelength is very short, the size of wave packet can be made very small, and this wave packet can follow the classical path. However, this is not trivial from the point of view of mathematics, because the wave packet spread anyhow, whatever wavelength is, especially for like a chaotic system. One can see that formally the wave packet spread so on. So this is not trivial. But in addition to that, if we want to try to push up quantum mechanics at the limit of classical object, we get then it's a paradoxical situation. It is well known. I'm sorry for expert. It is the Schrödinger paradox. It was invented by Schrödinger, so it's not the cut of Schrödinger. So let us suppose that there is a nucleus which decay. Okay. And if decay, we know that, as I saw, at the beginning of the decay, there will be linear combination of non-decay state and decay state. Suppose now that the decay state move a lever which make wreck an ampolla where there is a poison. So at the beginning there is this one. Then when the path follow is a linear combination of non-decay, still non-decay, and decay state with a broken ampolla. In this, if the no, so this is at this point there is a linear combination, if you follow Schrödinger equation, of this of non-decay and the crushed ampolla. Still linear combination. This propagates in the linear combination of dead and alive cut. So this part will kill the cut. The other part, when there is no decay yet, but the atom is still, the nucleus is still there, and not decay is a lie. So to get a linear superposition of that and the lie cut, of course, is a paradox. I think it can be considered a paradox. Another way could be to enclose everything in a box and then open at the moment of opening, the reduction takes place. But this means that opening the box, you can kill the cat just by opening. That is a paradox. So one cannot so easily, at least, extend to quantum mechanics at the macroscopic level, classical macroscopic. We get paradoxical situation. There must be a point where quantum mechanics go to the classical mechanics, where, I don't know. So this finished the 4 points I want to speak about. So again, could be elementary, but that is not the 4 point. The second part, the talk will be, first let us comment about the Copenhagen interpretation. How to solve this critical point? Just postulate that they happen and forget about everything. You can summarize this interpretation with a line in the Divina Commedia, where is written "State contentium agenda quia," which means don't ask too many questions. Here, the Copenhagen interpretation is you have not to ask questions. This is a talk by a word by his master Virgilius. Dante was asking too many questions. What? Why that? Why that? Why that? He said, "This is the will of God." So don't ask too many questions. I think translated in a more physical language means that all the phenomena must be described in terms of macroscopic terms. When we do an arrangement to make an experiment, we record the result. We change the arrangement, we record the result. And that's what we can do most. We cannot do more than that. Of course, if you take literally, this attitude is not interpretation, it's an attitude. We can do only phenomenology, we cannot do anything else. But above all, this is not what we do every day. We use wave packet, wave function, reduction, Bond's law, and so on. So we violate every day Schrödinger equation. Every day, almost every day. This is well stressed in this book by Belloc, this stressing these 2 points. I recommend this book, it's very good. So let us do the second part, that is the model. The model starts from the first observation, is that there are natural number, fractional number, real number, and there is non-standard theory, non-standard analysis, which say that you can go further and consider infinitesimal number and unlimited number, and consider them include in analysis. So these infinitesimal are not, have no measure, okay, but they exist. And to each real number, in this case 1, you can associate all the numbers which are differ by 1 by an infinitesimal, I call epsilon. And this form what is called a monad. So each real number is surrounded by a cloud of infinitesimal. And what is more important is that the non-standard axis is joined the union for all monads. This means that we are able to divide the axis, the real axis in a small interval of infinitesimal size. It's the dream of dividing a straight line in point, single point. It's not possible. This is the realization of that. This, I suppose that now reality needs that. So also the coordinate, time coordinate, need to include this monad. There is no hypothesis here. This is a rigorous mathematical theory. Mathematical. The hypothesis comes here when I introduce a lattice. I mean, I suppose that instead of the continuum of a non-standard continuum, I introduce a lattice of infinitesimal step. And this will be the manifold where all physical phenomena can occur. That is the hypothesis. And strangely enough, I realized after I knew everything, I did everything, somebody else did that for completely different reasons. So it's just a coincidence. So we have this lattice, one for each coordinate, one for the time coordinate. The basic remark is the following. All the physical quantities we can measure are in the standard sector, because the infinitesimal has no measure, no mathematical measure, and no physical measure. Mathematical, one can question. But despite although they are infinitesimal, they can play a role in the dynamics, as I will show. So let us extend the wave equation. Let us say Schrödinger equation, but actually in the non-standard sector is the ultra-relativistic limit. So then, if there is this lattice, then we get in unlimited frequencies, infinitesimal wavelength. We cannot speak of energy because otherwise we got infinite energy. So we have a wave function that are containing unlimited frequencies, but no energy. So it's an extension of the functional space, and so also each wave function has one component in the standard sector and one component, new one, in the non-standard sector. And a state represented not only by standard, but also non-standard. So this represents a state, quantum state. The non-standard part can be written in this way, which solves the wave equation. With some caution, but however. The important thing to notice that the overlap between two non-standard parts is proportional to the standard part overlap. So if we want to a new functional space, really, this set of unlimited frequency must be unlimited too, so that the norm, say, is not a norm, is infinite. Of course, all of you are scared at this point. Normalization. Finite normalization. And this shows that it cannot be infinite. So to use infinitesimal number, not scaling, but according to non-standard theory, these are legitimate numbers to be treated carefully, of course, but can be used. So let us go now to the interaction between two components, non-standard component of two states, is introduced automatically. Unlimited frequencies, but this is in the non-standard sector. What we observe is in standard sector. So we must do some trick to pass from the non-standard sector to the standard one. And this can be used, this way can be, what can be used is what in statistical mechanics is the cross-graining. So we divided the space into cells, and where there is only microscopic configuration, and where the density matrix is diagonal, in the sense that all the configuration have the same probability. This is the way of cross-graining. Why we do cross-graining? Because we don't need to observe microscopic description. So the statistical mechanics pass from microscopic description to the macroscopic description. That's in every textbook. And this can be done by cross-graining. And the same thing, not exactly the analogy, can be done to pass from the non-standard sector to the standard sector. So the non-standard sector is like a microscopic world. The standard sector is a macroscopic one, but still can be quantum. So in some sense, this non-standard part is a subquantum. In some sense, subquantum, substrate. And we can pass from here to here. If you do that, it can be done. I don't know in detail. This implies necessarily a stochastic process, and which is a function of the standard part of the time. This is time in the standard sector, so it's a real number, not standard real number. So I get a function which is of the coordinate of the time, standard time, so it's the usual function, but is extended to a non-standard part. This, what comes is that is a non-standard representation of a stochastic process in standard sector. Okay, this is the role of the infinitesimal in determining the evolution. If you take the standard part of this process, this come out to be integrating, integrating this way, you get what is called a Brownian process or stochastic process in the standard sector. So from the non-standard sector, we get up on usual standard sector by introducing this stochastic process, which indeed has the properties of a Brownian motion, which the main properties is this one. This is the variance, and the variance proportional to the standard differential, properly normalized. This means that each of dB step, say this is the step, is proportional to square root of it. That is what is happen, for instance, in a diffusion process, no? Where the delay, no, the diffusion length is proportional to square root of the time. Okay, so that is a standard Ito process, nothing new. Last step, we need to go from this process to the dynamics. How this process which is the process of the matrix element into non-standard factor, how it affects the total evolution. There is actually a very simple way to do that, just by requiring that the norm of the standard part of the wave function, let us go back. Yeah, this is the standard part. Yeah. This is the usual wave function. Having both this, the norm of this is conserved in time. And that is essential. It's a requirement which is you cannot avoid. Because first of all, if this is the state must have a definite norm. It cannot disappear or expand. And second, we need to reproduce quantum mechanics. So by requiring that the norm is conserved, well, one gets this equation, again, without further assumption. There is no assumption here. What happens is that the single state is a pure state, as the usual evolution by Schrödinger equation, plus a stochastic motion, which is, here is the interaction representation, so only the stochastic part is present. With the FLM to find some finite number that I will specify. Well, if you do that, what happens is that this equation produce at the basis of reduction, unicity, and Borneo. You get all of it. So we get quantum mechanics. We get quantum mechanics, but something which is subquantum in a sense, in some sense, like too literally, but in some sense. So this explanation, okay, why it is enough to explain. Okay, let us repeat. So this is the stochastic equation, which was obtained by Schrödinger here, and the Schrödinger of the interaction. And the Schrödinger comes from the fact that we extended the functional space. Okay, so again, we extend, we get the interaction which will contain, non-standard interaction which contain unlimited frequency. This is, if you do Schrödinger, you get a stochastic process, because we are speaking about time. And from the stochastic process requiring conservation norm, we get this equation which contains a reduction unicity. Gratis, without any other assumption. Okay. How now, with this new equation, the four critical points can be explained. Okay, I will. Okay. To do this, we have to look more carefully, more closely to the interaction between two non-standard parts. What are the ingredients, just the strength of the interaction, which is necessarily infinitesimal because include unlimited wave numbers, is the denominator, but this factor which was, I'm sorry, this factor here, is actually this, and increase exponentially with an unlimited number of non-standard vectors. So if the number of degrees of freedom, independent degrees of freedom, is small, this FLN is infinitesimal at a stochastic dynamics plane or as soon as the number of degrees of freedom increase, this factor becomes unlimited, and then dominant one. Again, you can be uneasy to use infinitesimal and unlimited numbers. Again, non-standard analysis allow you to do. Great. Now, what first critical point, measurement. How to proceed the measurement according to the new equation. So let us start with a linear superposition. This linear superposition, until Schrödinger equation is valid, is a linear superposition of the response. This fixes the representation. So this fixes also the meaning of detector. What is detector? It's the one which has this answer, this behavior. Now, if you want a real detector, the response of each measurement must, the signals of the detector must go to microscopic size. That everybody agrees on that. Otherwise, not a detector. If you go to the microscopic size, the number of degrees of freedom can overpass the critical value, which you don't know, but it must exist. And then you get the measurement, unicity, probability. So in each measurement, this part is for each one, single one. It's not a set of measurements, it's a single one. Second, spontaneous emission. For this, we need, okay, I need invoke vacuum fluctuations. The vacuum fluctuations are real things because they are responsible for the lamp shift, the Casimir effect, and so on. Now the vacuum fluctuation must include some non-standard component, and this non-standard component turns out to be able to create a reduction of the system. So from the linear superposition of excited and decay state, this is interaction, this fluctuation produce reduction, possible reduction, or reduction. And this is turned out to be reject the usual law. It was assumed the postulate. Okay, so is a spontaneous emission come out also from the same equations, provided we introduce vacuum fluctuation, which exists. Now, important thing to stress that if you have only the standard part cannot produce reduction. The standard part must follow ordinary quantum mechanics or Schrödinger equation, where there is no reduction. So we need a non-standard part. Okay. Reduction without interaction is the same. It's the inverse of the emission. So, and the interaction of the non-standard part of the vacuum fluctuation with the atom is what we have called before either interaction. So there is an either interaction which produces reduction. Classical limit can be done in this framework, the same framework, just because at the critical side, all superposition, quantum superposition, must disappear in any representation. This is a prediction of the model. There must be a sharp transition from quantum mechanics to classical mechanics. About entanglement, I only make a comment and tell a story at a survey meeting at a conference of a famous 1927, I remember, or 23. There was a meeting, gave the photo at the coffee machine, no? The one photo which is there. And during the discussion, Einstein get up and make this drawing, similar to like this drawing. He say, suppose we have all diffraction and then a screen here. So the wave packet, the wave function will be spread all around. If now I put a detector here, I detect the particle, then since originally the wave packet was, the wave function was spread, the wave function here disappeared. So you say something has happened in B. So what exactly happened? This cannot be checked because in this experiment, because or you check, you get the particle here, or you get the particle here. But if you do the APR experiment, you have two particle objects, and then you can get reduction, using reduction extension of the wave, you get entanglement automatically. Must be present. The observation I want to say is that the correlation which you get in APR can be calculated within standard quantum mechanics. And what is assumed is the wave function. One uses the wave function and instantaneous reduction. So in a sense, since the correlation is absolutely correct, has been checked with great precision in different conditions, so in some sense, entanglement gives legitimacy to the wave function. We can speak wave function if we want to calculate. Otherwise, forget about it. So, summary. The basic assumption of the model is extension of space-time manifold and deduction of a lattice. The other assumptions, there are other assumptions, but are coherent with the rest and are needed, are natural if we want to have a coherent view. And the critical point somehow solved. How to check the model, of course. We have to keep in mind first that the model was devised to solve the critical point. That's the first check of the model. Other check can be done. For instance, with spontaneous decay. If you look at not written well here, at the occupation number of the excited state, which can be checked. This is, if the model is correct, this will fluctuate somehow, and this can be checked by tomography, homodine detection, fluorescence emission, is discussed in this paper. The other possibility is to observe a possible sharp transition from quantum mechanics to classical mechanics. And these are experiments which can be done. And people are doing. I am quoting this, but there are many others. And it's the superposition of two acoustic models. They can check if the superposition persists as the intensity, so the number of particles involved increase. And they say that up to macroscopic objects like 10 to the 16 particle, the superposition survives. This is misleading because, according to the model, what matter is not the number of particles, but a number of independent degrees of freedom, which in the case of acoustic wave is only one, because it's a collective variable. So there cannot be any collapse or reduction. So one has to be careful. The same tree with the superposition of location, center of mass, and the same thing. It's only one degree of freedom. So the number of variables we need to describe the wave function. Here is one. I cannot. So my moral is, don't listen to Virgilius. Ask questions, because there are never too many. And without question, we cannot do real progress. Sorry for that. That is all.